So we've now seen the derivation of the ordinary least squares solution, and we turn to looking at a derivation of the weighted total least squares solution, which is quite different. So the total least squares approach assumes that there are errors both on the x values and the y values when we're fitting a line. The equation that we use to denote that is that we have this y vector of measurements, noisy measurements, so there's kind of a truth there on this delta y, and then this x vector of noisy measurements and a delta x to a line with slope q. Try to illustrate this on the right. Now the measurement point is shown like this with error bars in both dimensions, and the error bars don't have to be the same width in either dimension. They don't have to be the same from point to point, and so forth. So you can see this one has quite a lot of error in the x direction, and this one has quite a lot of relative error in the y direction, and the other two have fairly similar errors in the x and the y directions as drawn. And the goal is to put a line through that data that minimizes, in some sense, the x distance between the point and the line and the y distance between the point and the line. So it's not the y distance only, but we want to do it in such a way that we keep in mind these standard deviations of the noise in the x direction and the y direction. In our approach, although it's not obvious here, it really becomes a little bit more necessary when we look at the goodness of fit metrics and so forth in the next section. But we assume that our delta x are zero mean and that they're Gaussian, and that the variances are known, and the same for y, that they're zero mean and they're Gaussian, and the variances are known. But the variances do not need to be the same between x and y, or for any one point to any other point. Total least squares attempts to find this slope of a line, q hat, of the true cell total capacity q. So the truth is q, the estimate is q hat, and we are doing so by minimizing the sum of squared errors, delta xi, plus the sum of squared errors, delta yi. Except we could do that, that would be fine, but we're going to be a little bit more general than that, and we're going to weight the errors in the x direction and y direction by the standard deviation of the measurement error in each direction. So we will take into account the uncertainty of the measurement. Here is our merit function, or cost function, for weighted total least squares. Remember, we use a very similar notation to before. Little xi is the measurement point, and capital Xi is where that measurement maps to on the straight line. And little yi is the measurement point, and capital Yi is where it maps to on the straight line. So xi minus capital Xi squared is the distance between the point and the line, and we're dividing by the variance in order to normalize it. And the same with y, excuse me. We have a little different idea here, though. Going back to the picture, when we were looking at the regular least squares, the ordinary least squares, we said that the x was perfect, so I would take a little yi and make a capital Yi like this, using exactly the same value of x. Now we are no longer assuming that x is perfect. The measurement is perfect, and so the data point, xi, yi, so I've got xi, comma, yi, now maps to some point on the line, capital Xi, capital Yi, and that point on the line may not be directly underneath x. It may be shifted over, and they may be different for every point, how that's done. So the optimization then is going to create a way to map each measurement point to a line point that's consistent, and we'll try to then minimize the squared weighted distances between little x and little y and big Y. And we'll see how that works out in the math. Okay, so we do have this equation that big Y equals Q hat times big X. Those are points on the line. Little x, little y are measurement points, and there's a mapping that we're going to have to make between little x and big X and so forth. And then we're going to optimize that mapping using this weighted total least squares cost function. In order to enforce the linear form of answer, this form right here, we employ Lagrange multipliers in our cost function. And as you've probably seen these in other courses, especially a math course, I won't belabor the point too much, but the idea generally is that this is zero. So I'm not really adding anything of consequence to the cost function. I'm adding zero to the cost function, but I'm adding zero in such a way that when you go through the math, it enforces that being zero in the cost function, and we'll see exactly where that happens. So we use the Lagrange multiplier there, and we have an augmented, the comma A is an augmented weighted total least squares cost function. This part is exactly the same, but I have a lambda I and then y minus qx, which is this constraint placed in right there. In order to optimize a cost function, what we're going to do is we are going to take derivatives, partial derivatives of the cost function with respect to the unknown variables in it. Not q yet, q comes later, but we're going to take derivatives with respect to the capital X, capital Y, and lambda, and set those derivatives equal to 0. So first, taking the derivative with respect to lambda, we can see that we're going to get this term. So I have, minus yi minus q hat times xi equals 0. And we solve that, and we get yi equals q hat xi. Now this always happens with Lagrange multipliers. It's why they work. When I take derivatives with respect to the lambda, we get one equation that must be satisfied in the result, which is the constraint we were trying to have as one of the equations that's satisfied in the result. However, it's done in such a way that this lambda factors into the other derivatives and basically folds this constraint into the other solutions as well. It's really a very clever kind of thing. When I take derivatives with respect to capital YI, that's going to be in this term. So I get the minus 2yi times little y minus big Y all over sigma squared. But it's also in this term, so I have minus lambda I as well, equals 0. And that lets me solve for lambda, just bringing this over to the other side. It gives me lambda I equals minus 2 little y minus big Y over sigma y squared. And then I take derivatives with respect to the xi. So it shows up here first. It also shows up there. So it's going to be minus 2 little x minus big X over sigma x squared. And this is getting really messy. But you can see when I take the derivative of that term with respect to x, it's going to be plus lambda times q hat. And that's equal to 0. In the next line, I keep this term unchanged, but I take my solution for lambda, which is this, and I plug it in right there. So the q hat stays, and I plug in my solution for lambda, which is minus 2 little y minus big Y over sigma y squared. Notice this is not inside a summation. We took derivatives with respect to a single term in the summation, So with respect to that term and setting the derivatives to 0, I don't have to worry about the index quite the same way as I did before, and I am permitted to multiply both sides of this equation by, for example, sigma x squared and sigma y squared, which I do to clear up the fractions. So when I multiply both sides by this, the left side is still 0, but I get a sigma x squared in there. When I multiply both sides by this, the left is still 0, but I get a sigma y squared there. And we can see that. And I also multiplied both sides by -1 to clear the minus sign. The next thing I did was to expand. So expand the first term and expand the second term. And that allows me to solve here for the xi by combining this and bringing it to the left-hand side and then dividing by the factor. So I have that capital Xi is equal to little xi sigma y squared q hat little yi, etc. You can see it in the box. But what is important about this is I have solved for the x-coordinate mapping of my data point in terms of the measurements, in terms of things I know, and q hat, which I don't know. So basically, I've made my mapping. And if we plug this into here, which is another equation that must be satisfied, we said, I have yi again in terms of measurements only and of q hat. And that's critical. I now have a deterministic mapping between my little x, little y, and big X, big Y. And I don't have to use the big X, big Y anymore in the solution. I can rewrite the merit function in terms of things that are measured. This was the original merit function. I'm going to put this in here and in here with a q in it because that's what y is. There's a few lines of algebra here which look a little bit messy. They're not too bad. Again, this is the solution for capital Xi, and this here is the solution for capital Yi. To go to the next line, I notice that this term, sigma y squared plus q squared sigma x squared, is the same there. So I'm going to multiply the numerator and denominator of both fractions by that thing squared in order to clear it from the numerator of each one of those fractions. So we can see that inside the squared of the first thing, I've got the xi multiplied by that, and then this here multiplied by that clears the fraction. But in the denominator, the sigma xi had to be multiplied by that thing squared. And similarly over here, I have the yi, but when I multiply by this squared, that comes up there. And then the q hat remains. The numerator now is by itself, and the denominator used to be the sigma yi, and now it's multiplied by that term squared, and we get this. That's just a little bit of algebra. Now we factor some things out. I'm doing a few lines of things here and condensing a few things here. Actually, maybe I'm not. Let's look at this carefully. I have an x sigma y and a minus x sigma y, so those cancel out. So what I'm left with, it looks like I'm left with this here still multiplied by xi, so that's going to be one term, and then minus q hat yi times sigma xi squared. If I combine these two terms, they have a common sigma xi squared in both of them, and one of the q's is common, not both, but one of the q's is common. So I can factor that out. Notice there's a squared, so I'm going to square it when I factor it out. So the sigma x squared squared is sigma x to the 4, and one of the q's, when I factor it out and square it, I get q squared. And what's left is it's really xq minus y squared, but since it's squared, I can write it as y minus qx squared, the same thing. And that is that numerator. The denominator term I left alone. And we did something similar here, I believe. Let's have a look. We have so I've got a yi sigma yi squared, which is going to be combined with the minus qxi times sigma y squared. So the sigma y squared can come out of that term, and the other term has a so I've got a y q squared sigma x squared, and I've got a minus q squared y sigma x squared. That goes away. So so this term basically is going to cancel out when it's multiplied through, and I'm left with the other one. And out of that one, I can pull out this sigma y squared. It gives me sigma y to the 4th, and then y minus this qxi term squared. Looking at these, they have the same denominator, sort of, except this one has a sigma x squared in it, and this one has a sigma y squared in it. However, the sigma x squared, look at the numerator, there's a sigma x to the 4th, so that cancels, and that becomes squared. And the other one, this cancels, and this becomes squared, and now I do have the same denominator. And look at the numerator. Both numerators share a y minus qx squared, and what's left over is q squared sigma x squared plus sigma y squared, which is the same as one of the terms in the denominator. So it cancels the squared in the denominator, and it just leaves a one of those in the denominator. So at the end of all of this, I have the cost function for weighted total least squares is the sum, I equals 1 to n, yi minus qxi all squared over q squared sigma x squared plus sigma y squared. That was not at all obvious. We started out with this function here, which was intuitive, I think. We're minimizing x distances squared and y distances squared. That's our goal. But we had no way in this equation of doing the minimization because we didn't know what capital X and capital Y happened to be. So we had to enforce them to be on a line. We did that, and that allowed us to replace capital X and capital Y with a different expression in terms of lowercase and lowercase y, and gives us finally this cost function. Haven't optimized the cost function yet, but it actually gives me the cost function that I need to minimize, and this is the computable one. Now the numerator, maybe we could have figured out the denominator of this. Probably not. In order to actually find the q, we take this cost function and we take the partial derivative with respect to q hat and set that partial derivative to 0. Now this is different. When we were finding the capital X and capital Y, remember we did not take the derivative with respect to q. We did it with respect to lambda, y, and x, but not q. So we are getting new information here. We set this derivative equal to 0, and the math begins to get fairly tricky because I've got a q in the numerator and a q in the denominator now, and so I can't, and q in the denominator is going to multiply an I term. I can't just factor the q out anymore, and it becomes really quite tricky. And we're going to be doing a lot of math from now on using Mathematica and just stating what the answer is rather than trying to go through line by line by hand. There's not maybe too much to be gained, not too much insight to be gained by doing it by hand, and Mathematica gives us an answer that I think we can assume is always correct, whereas by hand it's easy to make mistakes. Taking the derivative with respect to q, we get this summation, and that summation we set equal to 0, and there's no way to solve it closed form. The q is buried. I can't multiply both sides by this because there's i's in here. It's going to be different for every summation index. It's not going to be the same, and it's the summation that equals 0. It's not the individual elements that equal 0. So we've lost some nice properties of the weighted least squares solution. And over the next couple pages, we itemize the nice properties we claimed for the weighted least squares solution and how they no longer exist for the total least squares, weighted total least squares solution. So first, there's no closed form solution. Just doesn't exist. We have to use some numeric method. And one way to solve numerically, whenever you have a cost function, you could plot it like this. If it's versus one variable, your, say, squiggle variable, and you want to find, and this is f of squiggle, and you want to find the value of squiggle that optimizes this, you can start out here, and you can find the gradient at that point, the slope, and then take a step in the direction of the negative gradient, and you find the next point, and the next point, and the next point, and you eventually converge to near the minimum. That's called a gradient descent method. They always will find, well, if you're careful with your step size, they'll always find a local minima. They're not guaranteed to find a global minima in a very complicated function, but they do work, but they're kind of slow. A variation of that would be to find the slope, but also the curvature. If there's very little curvature, that means we're on a fairly straight line, and we can take a big step. But if there's a lot of curvature, we need to take a smaller step because it means we're close, relatively close to the minima. So the Newton-Raphson method finds the slope, and it finds the local second derivative too, to find the curvature, and basically fits a parabola, locally fits a parabola based on this local information. And the local parabola might look like that, and then it jumps immediately, or at least some methods, either immediately to the bottom of that parabola because it knows where the minimum of the parabola is, or at least it takes a good healthy step towards the direction of that, and then it looks for this point, and then which is really that point, and then it fits another local parabola, and it can much more quickly converge to a local minima than just pure gradient descent. To use Newton-Raphson method, we need to know what is the local slope and what is the local curvature, or second derivative, which is called the Hessian. And I'm going to show you what those are because they will be useful when we do use the weighted total least squares method in an example later on. We have to solve using some method like that. And it's also going to be useful in one other place. So having pre-computed what this second derivative is going to be of value to us. This is how the Newton-Raphson method works. K is an iteration at the present time step. So we have time equals 1 dot dot n dot dot capital N. We're thinking so n is our time variable, but within any one of these times I've got k equals 1 to whatever, capital K, of performing an iteration, a number of iterations to search for the best optimum Q had at given data up until this point in time. So K is not a time index, it's a Newton-Raphson index. So q hat of k is q hat of k minus 1 minus the, be careful, this is the partial of the cost function with respect to q, so that's the gradient, otherwise known as the Jacobian. And the denominator is the second partial derivative, and that's known as the Hessian. So it's the Jacobian divided by the Hessian, or the first derivative divided by the second derivative. The first derivative we found, by the way, it's this. It's that whole summation. So if we had an estimate of q hat at this particular point in time, we know all of the x's and the y's and the sigmas, so we put our estimate of q hat in there, we do that summation, that gives us the numerator term. The Hessian is the second derivative, and again we're using Mathematica here, and it gives us this equation. It's not particularly beautiful, but it's perfectly computable. Again, I just stick my q hat k minus 1 estimate in there, and I compute a number, and the numerator, the Jacobian gives me a number for the numerator, the Hessian gives me a number for the denominator. They're both just numbers. I divide them, and that updates my q hat estimate. That's how the Newton-Raphson method works. We could initialize it with maybe a weighted least squares estimate. We know it's biased, but it's probably at least close to the truth. And the Newton-Raphson method has a pretty nice property. If you have to do an iterative method, it's quite nice, that the number of significant figures in your answer doubles with every iteration k of the update. So if I had one significant figure at k equals 1, then I would have 2, then 4, then 8, then 16, then 32, and so forth. So with a very small number of iterations, we get accelerating accuracy of our solution. We don't need to do this too many times. Practice shows that maybe 4 iterations gives us double precision results, or maybe 3 iterations gives us single precision results, if that's what we're looking for. So ugly equation, but not really that bad computationally to do this. Technically speaking, this metric function is convex, which means that, among other things, that there is only one minima to the function. That minima is a global minima, so if I find the minima, then I know I've found the best overall optimal solution, and therefore this method is guaranteed to converge to the global solution, not only some kind of local semi-optimal solution to it. So point number 1, there is no closed form solution. We can find a solution, but it's a numeric method, which takes some time. Point number 2, there's no recursive update. Now, this is even more disappointing because this has some storage implications and computational implications. In terms of storage, I have to keep the entire vector x and y. I can't somehow fold the last data samples all together into my estimate and then have a simple update from one measurement to the next measurement. I actually have to keep the entire history and apply this entire optimization to the entire history. So storage grows. If I have only a few data points, maybe that's not a big deal, but if I have a battery pack that's supposed to operate for a decade and I update once a day, well, that's a lot of data points that you have to store. If I update faster than once a day, it's even more. And what's even more troubling is that the computation grows as the number of data points grows. If you look at this, every time I do this, I sum up all the data in my memory, and same here. These equations, the first time I do them, it's 1 summation index. The next time it's 2, 3, 4. So computation is going to grow linearly, and that means that if I plan over the life of my battery pack for a certain number of updates, I have to be able to have a big enough, fast enough processor to handle the end-of-life update, not only the beginning-of-life update, which is quite fast. So overall, this is just not well suited for some kind of embedded system application that has to run in real time with limited storage and limited computation capabilities. We'd really like to find a recursive solution. And what we're going to do before the end of the chapter is we're going to find an approximate recursive solution that does quite well. There's no recursive update, so there's no fading memory recursive update. But we can do non-recursive by defining the cost function as before, but inserting this fading memory in the cost function right there. And everything is essentially the same except the Jacobian is this and the Hessian is this. There's slight changes there if we're going to do this Newton-Raphson method. So this is disappointing. We haven't really yet shown a result that shows the bias of the ordinary least squares solution, but at least you can see in the derivation that nowhere in the derivation do we take into account a variation of x. So you might at least be able to see that there could be a problem if there is a variation in x, whereas the total least squares solution takes that into account explicitly, so that should be better. So we don't know how much better the total least squares is going to be versus the ordinary least squares, but we have at least this thought that it should be better. But it doesn't have any of the nice computational properties. It's not recursive, it's not, and it's not finite memory. It's not closed form. In a little while, in a few sections, we will address a special case of weighted total least squares that does give a closed form solution with recursive update and fading memory. So it's still a total least square solution, but it's a special case. And then we will look at that special case and use that to motivate an approximate solution to the general weighted total least squares. So a true solution to the special case gives an approximate solution to the general case that also has these nice properties. So all hope is not lost. There is a lot of hope. We will get to that. But before we do, I'd like to consider some properties of both of these solutions that allows us to just to be able to evaluate, is it a good solution or is it a bad solution? Because we're going to need that in order to make judgments later on.